Let's take an example in 2D so we can draw it better. Last time we used the notation L of t, L standing for line. We were parameterizing lines. But more generally, the notation for a general position vector is R of t. And let's make it be a fairly simple example. Component functions f of t and g of t. And let's let those be t squared and t cubed. So fairly simple. As I've emphasized before, lots already, you can graph this as a parametric curve, but you also, even more importantly now, is graph the position vector itself. If you graph this particular parametric curve in the XY plane, what you're going to see is something that looks about like this. And what's the motion going to be like? Think about it with me. As t increases, starting with negative values of t, when t is negative, t squared is positive, x is positive, and y t cubed is negative. Y is negative. You're down here where x is positive and y is negative. As t increases, x goes towards 0. You move to the left, and y is increasing. We got to be moving to the northwest here. Evidently, we're at the origin when t is 0. And then as t increases past 0, we go up to the northeast. But I did draw this to look like maybe there's a corner in the graph here, and there is. There's a cusp there. This is not a smooth curve. But at any moment in time, say I'm right there, that's R of t at some particular moment in time, I can draw a position vector for that point, an arrow going from the origin to that point. So effectively, I'm equating points with vectors. I'm using R of t to denote not only the point, but also the arrow. Technically speaking, if I wanted to be extra picky about it, I'd say the point has coordinates xy equals t squared, t cubed, and the vector has components xy equals t squared, t cubed. The fact that they're technically different mathematical objects, points versus arrows, is what makes it worth it, to our author at least, to use slightly different notation. Parentheses for points, pointy braces for vectors. But I will tell you, in other books, sometimes people don't bother you. They use the same notation for both. Maybe parentheses for both, maybe pointy brackets for both, maybe even square brackets for both. Notation varies wildly on these points from book to book. As t changes, as t increases, the point moves, and the position vector moves. Well, if I keep its initial point, its base at the origin, that stays the same, but it changes direction and length. When t is negative and far from 0, it's a long vector pointing down that way. When t is closer to 0, it's a short vector pointing about like that. When t is still negative, though, when t is 0, it's the 0 vector. It's just a dot, an arrow with no length or direction. T is slightly positive. It looks like this. When t gets bigger, it gets longer and longer. So the arrow itself is changing. The calculus that we're about to describe is the calculus of that changing arrow. It's a vector-valued function. Calculus of vector-valued functions. What can we do to do calculus for these vector-valued functions? We can take limits. For example, what's the limit of this function as t approaches some number like 2? How do you compute such a limit? You compute it component by component, component wise. Effectively bring the limit sign into the brackets here. Why? Because it's a definition that makes sense. It's not something to prove. This is a definition that makes sense. It's a good definition because it helps us make sense and interpret these vector valued functions. What does this equal for this example? It equals the limit as t goes to 2 of the first component, t squared, comma, the limit as t goes to 2 of the second component, t cubed. Both of those functions, t squared and t cubed, are continuous. Therefore, you can evaluate this limit just by substitution. Plug in t equals 2. Might seem like a trivial point, but it is worth mentioning. It is worth emphasizing. So the limiting vector here is 4, 8, which does happen to equal the function value at t equals 2. This is r of 2. And the equality of the original limit with the function value at 2 is what's a symbolic, that's the symbolic meaning of continuity. R of t is continuous at 2. In fact, it's continuous everywhere. R of t is continuous for all t. Why? Because the limit as t approaches any particular number, call it t naught of r of t, equals r of that number, t naught. And why is that the case? Because it's also true for each of the component functions. We're doing things component by component. The next question we ask in calculus after we talk about whether the limit exists and whether the function is continuous, the next step up is the function differentiable? Does the derivative exist? What is r prime of 2? Technically speaking, to include all possible examples, even strange examples, we have to go back to the limit definition of the derivative. Limit, as say h goes to 0, of same kind of difference quotient you see in calculus 1, except the function is vector valued. R of 2 plus h minus r of 2 divided by h. You should be able to calculate this kind of limit too. How? Do it component-wise, component by component. What's r of 2 plus h? Well, remember, the first component of r is t squared, the second component is t cubed. So that'll be a vector whose first component is 2 plus h squared and whose second component is 2 plus h cubed. R of 2 itself, as we found out previously, is the constant vector 4, 8. Divide by h. Simplify. I could subtract these vectors component-wise. Dividing by h is the same as multiplying by 1 over h. I can bring that scalar into each component as well. So if I do both of those things at once, I get these kinds of things. I subtracted the vectors first, component-wise. Then I multiplied both vectors by 1 over h, component by component. And for extra emphasis, we should technically bring the limit sign in to both. like this, just doing every step we can think of to confirm that technically all these things need to be defined. And then you compute each of those limits. There's two limits to compute. So this is Calc 1 now, just component by component. Remember doing this in Calc 1, 2 plus h quantity squared is 4 plus 4h plus h squared. Don't forget to subtract 4. 2 plus h quantity cubed is a bit trickier. I'm going to be thinking about Pascal's triangle in my head. We're expanding the cube of a binomial. The coefficients come from Pascal's triangle. You remember this? That kind of thing. For cubes, it's this row. The coefficients come from that row, 1, 3, 3, 1. But careful, one of the things that's in the binomial is a 2. The other is an h. The first term that I'm going to get after I expand this is going to be 1 times 2 cubed times h to the 0 power. H to the 0 power is 1. So I really just get 2 cubed, 8. Second term is going to be, listen carefully, 3, the next row, next number in this row of Pascal's triangle, times 2 squared times h to the first. 2 squared is 4, 3 times 4 is 12, plus 12h. Next, I get 3 times 2 to the first times h squared. 3 times 2, 6, times h squared. Next, I get 1 times 2 to the 0 power times h cubed. 2 to the 0 is 1. 1 times h cubed is h cubed. Minus 8, all divided by h. The constants in both cases end up canceling. With what's left, and h can be factored out like this. And like this. Oops, forgot my limit sign in this. Bad notation. Pointy brackets around the whole thing. Carry my limit sign here as well. Getting ahead of myself. Then we, at this point, you remember from Calc 1, you divide out the h's. And then with what's left, you can take the limit by using continuity, just plugging in h equals 0. The terms that do not involve h, well, the terms that do involve h go away. So we're left with 4, 12. In Calc 1, when I teach Calc 1, I really emphasize this step as being a key that you really should know a deep reason for that. Why are these two things equal? I mean, if we can't plug in h equals 0 here, in these two spots, why can we plug in h equals 0 here in the end? The answer is because these two expressions are equal as long as h is not 0, as well as these two expressions being equal when h is not 0. And technically speaking, if you look at the rigorous definition of the limit, which is the very first thing talked about in section 11.1, it doesn't matter what happens to the function at the value h is approaching. Here's what I'm talking about. I'll show it to you here. Remember seeing this kind of thing before? For any epsilon greater than 0, there exists a delta greater than 0, blah, 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 blah. What? Do I have to know that for the test? No, I probably won't put it on the test, but let's just think about it a little bit. What's this saying? For any small tolerance, epsilon, distance within the limiting value. This represents the distance between R of t and the limiting value. I can make that as small as I like, as long as t is within delta of c, close enough to c, but not necessarily equal to c. R of t is defined on some interval, except possibly at c. What is c for our problem here? C is what h is approaching, 0. H is like the t. We're letting h go to 0, t go to c. These functions of h are not defined at h equals 0, but it's irrelevant. They're equal to these things when h is not 0, so these limits are the same. It's irrelevant that these are undefined at h equals 0. Their graphs look like the graphs of these things as functions of h, except with holes in them, points missing at h equals 0. Doesn't matter, the limit still exists and still equals this vector here, using the continuity of these functions at h equals 0. Maybe that went over your head. Maybe you're like, oh yeah, I guess I get it. But hey, I don't need to know it for the test. Yeah, it's not something I'm going to emphasize in the test. But realize that is technically the real important step right there. More important for us, though, is how to interpret this vector. So this is r prime of 2. How do you interpret it? What was r of 2 again itself? R of 2 had components 4, 8. How do you interpret these two pieces of information? This is the most important thing. When we're plotting this curve at t equals 2, the way I plotted this, the scales and the axes are not the same. This would be x equals 4, y equals 8. Maybe I should try to draw it more accurately. Let's try to draw it more accurately. If this is 4 and this is 8, we're at this point when t equals 2. That's the point we're at when t equals 2. The position vector from the origin to that point is that vector, that arrow right there, that has components 4, 8. R prime of 2, this vector 4, 12, has those components. How do you interpret that? You draw it with its initial point, not at the origin, but at the location of the object at that moment in time. And it will be tangent to the curve. It'll have components 4, 12, so it'll be longer than I drew it. If I try to draw it accurately, it's going to go 4 units to the right and 12 units up from 8, which technically speaking would put us way up here. 8, 16, maybe right around there or something is 20. Technically, it looks like this. Ignore that arrow. That is r prime of 2. And you want to visualize the derivative in that way. To start with its initial point at the location of the object. And if you do that, it will be tangent to the curve when the curve is smooth and have a length equal to the speed. The speed here at time 2 is really the length, the magnitude of the velocity vector at time 2. That's the square root of 4 squared plus 12 squared, which will be square root of 160, which if you want to simplify it is 4 square root of 10. Between 12 and 13 meters per second, say. But this should beg a question. Why is it tangent to the curve? And y does it have a length equal to the speed? We need to get more basic to help us understand why. To get more basic, we can talk about average velocity. This is the velocity vector too, by the way. We could call this v of 2, v for velocity vector. Why is that the velocity vector? Let's think about what the average velocity would be. Average velocity, not at some moment in time, but over some time interval, from t equals t naught to t equals t1, say. I think the book might use t1 and t2. Think back to how you learned about average velocity with, say, one-dimensional back and forth motion or something. You do displacement, change in position over time elapsed. Same idea happens here. It's still displacement over time elapsed. Maybe we call the displacement vector d for displacement. Time elapsed would be t1 minus t naught. Yeah, the displacement is a vector in 2- or 3-dimensional motion. Imagine 3-dimensional motion with me here. Okay, got a bug flying around, starts right here. Okay, keep track of that. I'll keep track with my left hand. Bug flies around all over the place, going back and forth, all over the place, ends right there. It traveled a very long distance to end right there. What's its displacement? What's its change in position? It's an arrow going from the starting point to the ending point. It's a fairly short arrow because it's ending close to where it started. That's the displacement vector. The average velocity vector then is to take that vector and divide by the amount of time elapsed. Now, if that's a long amount of time elapsed, you're really multiplying that vector by a number that's going to be small if the amount of time elapsed is large. If this bug flies around very slowly, ends where pretty close to where it started, small displacement vector, we're dividing by a large number, multiplying by a small number. This average velocity is going to be very small, but it will be in the direction of the displacement vector, right? Because it's a scalar multiple of the displacement vector. On the other hand, if the bug's flying very rapidly, not much time has elapsed, we're dividing by a small number here. If it was really small, we'd be multiplying by a big number. The displacement vector is like this long, but this average velocity vector could be much longer, but it's still pointing in the same direction. Good to get that kind of intuition. What happens with the average velocity if the bug ends where it started? It's zero. The displacement vector is zero. Even though the bug moved around, the displacement vector could be zero. The average velocity could be zero. It could be the zero vector. So it's good to think about those kind of extreme examples to understand what this concept is. But for our purposes, to understand why the velocity vector is tangent to the curve, we'll be happy drawing pictures. This is not proof, this is intuition. If that's the curve of motion, whether you could pretend this is a 2-dimensional drawing or maybe even a 3-dimensional drawing, here's your position vector at time 0 or time t naught instead, let's say. The motion's along the curve this way. Here's your position vector at some later time. That's r of t1. D is the difference R of T1 minus R of T naught. In other words, D plus R of T naught is R of T1, which means one way to interpret D geometrically is to draw it to start at the tip of R of T naught, the head of R of T naught, and end at the head of R of T1. That's D right there. Think about the head to tail geometric meaning of vector addition. D plus R of T naught has to equal R of T1 by the definition of what D is as a subtraction, as a vector difference. It's got to be that vector. And look, it's almost tangent to the curve already. Now do the typical thing you do in calculus in this context. Imagine letting T1 approach T naught. What's going to happen as T1 gets closer to T naught, this R of T1 vector is going to get closer and closer to R of T naught. And in the limit, well, the red vector is going to get closer and closer to being tangent to the curve. In the limit, as T1 goes to T naught, we get seemingly an R of a D vector that's tangent to the curve. But wait a minute. If R of T1 is getting closer and closer to R of T naught, isn't D also going to zero? The zero vector? And doesn't the zero vector have no direction? Yes, that's all true. But remember, with the velocity vector, which is the derivative of the position vector, we're really doing a limit not only of the displacement vector as T1 goes to T naught, or I should use better notation here, sorry. V of T naught, which is R prime of T naught, can be thought of as a limit as T1 goes to T naught of the displacement vector divided by T1 minus T naught. I'll explain why here in a second. So even though that displacement vector, yes, it's getting closer and closer to being tangent, while at the same time getting shorter and shorter, even though it's getting shorter and shorter, this average velocity is not necessarily getting shorter and shorter because we're taking a vector D that might be very small when T1 is close to T naught, but dividing it by a very small number, which multiplies it by a large number, which scales it up. This is not rigorous math. This is not proofs. It's just intuition. Effectively, in the end, even though D goes to zero, the velocity vector does have some finite length. But it is tangent to the curve because these D's are getting closer to being tangent. It's not a proof, but it's some intuition. I think it's worthwhile intuition. Why is this equal to the derivative? That looks like a different limit. Why are these equal to the same thing? By the way, D, remember, is this. Effectively, to see that this is the same as the original limit definition of the derivative, just let H equal T1 minus T naught. Then this gets replaced with an H. T1 gets replaced with a T naught plus H. That's what goes right there. And T1 going to T naught is the same as H going to zero. So this really is the same as the limit definition of the derivative, just different notation. We found the derivative for our example at time 2. We found the derivative at time 2. It was this vector 412. What's the derivative in general? We could do it with limits, but guess what? We don't need to. We're happy. If R of T is differentiable, meaning it has a derivative everywhere, then its derivative can be found just by differentiating the components. Do it component-wise again. So, for our example, R of t being t squared comma t cubed implies the velocity vector v of t, the derivative of the position vector, has components 2t comma 3t squared. It's a function of t as well. That velocity vector is changing in magnitude and direction as well. Let's visualize it now for this example. I've got kind of a standard way that I'd like you to approach these things. I would like you to define the f and g functions first. T squared and t cubed for our example. Just for clarity on the concepts. And define R of t after you defined f of t and g of t. You can do it like this. So if you need reminding, in Mathematica, when you first define functions, you need underscores. The colons that I'm using are optional. I'm using curly braces for my vectors, though Mathematica could interpret that either as a point or a vector, depending on the context. Semicolons, technically speaking, their function is to suppress output, but I like using it between my different lines of code effectively in these definitions of these functions. You can define next the velocity vector to be the derivative of the position vector like that. Use a prime like that. Notice once you've defined functions, do not use an underscore anymore. And hopefully you don't get failed. Probably something is saved in its memory that's messing it up. If something like that happens with when you do what I just did there, you can always quit the kernel to clear the memory. Though if you do clear the memory, then you need to re-enter stuff if you've entered a bunch of stuff. See if it works now. Okay, evidently it worked. To confirm it, we can type v of t and hit enter and see if we get 2t, 3t squared. Yep. We can also confirm our previous answers, R of 4, R of 2, 4, 8, and R prime of 2, 4, 12. We can confirm our limit. Limit R of t as t goes to 2. It's going to be 4, 8. We can confirm the limit of the difference quotient. Let's go ahead and, okay, let's do it this way. R of 2 plus h minus R of 2, all divided by h. H goes to 0. Make an arrow there with a minus sign and a greater than sign. Or 12, that's the derivative. So we can confirm all those things. We can use parametric plot to plot the curve itself. There we have it. But that's still not quite ideal because ideally we want to look at the motion. So, I mean, you're going to make printouts of your plots, so you can just do a parametric plot like that. But if I want to see the motion, put this inside, manipulate. I think I'm going to pick a smaller interval so it's not so extreme in its scale here. So I'm putting parametric plot inside manipulate. Manipulate makes animations of lots of things, including parametric plot. I'm going to start t at -2 instead of -3. And I'm going to make the right endpoint of this interval b. Common notation for a left endpoint is a and a right endpoint is b. That's why I use a b. And outside the parametric plot, I'll put a comma and curly brace, b starting at, say, -1.999 and going up to 2. Let's see what it looks like now. We're just going to see the curve itself. The scale is not constant. Mathematica will adjust the scale as we go, which is not ideal. So, yeah, maybe we want to fix the scale plot range, we'll do that. Oh, maybe -2 to 10 in the x direction, and something bigger in the y direction, like, I don't know, -10 to 10. That'll fix the scale. We'll see the motion be fast at first, then slow down as it approaches the origin. Here we go. Slowing down, slowing down, slowing down, then speeds up. We can plot a position vector in this picture as well. Gets trickier though. You will not have to do this for your homework. At least not right now. Show combines different graphics. I like to get an arrow, a position vector in there as the point moves. Unfortunately, the best way to do that's not real simple. Over here, I'm going to type graphics, put a comma between that and position the parametric plot. Inside of graphics, I'm going to put curly braces. Let's keep it simple. Arrow. Inside of arrow, I put more curly braces. 0, 0, which stands for the origin, and comma, R of B, which stands for the location of the object at time B. I'm using a B because that's the animation parameter. I want to see the arrow change as B changes. This will draw an arrow from the origin to R of B as B changes. So this should work. You can see it. Yep. It's always starting at the origin. Unfortunately, it got rid of the axes. It's always unfortunate when these kinds of things happen. You can add them back in there by doing comma axes arrow true. Seems like a shame to have to do that, but it's based on default values for various kinds of commands. So that's the position vector. It's a changing arrow, changing direction and magnitude as time goes by, as it has to be because the object's moving. What about a velocity vector? I can make another arrow, curly braces. But remember, with velocity vectors, I don't want to start at the origin. So I don't want to put a 0, 0 first. I want it to have its initial base point at the location of the object at time B, which is going to change over time. I want it to be RB for the initial point. Well, what about the ending point? Should I type V of B? Unfortunately, that doesn't quite work because of the way arrow works. You need to add on R of B to that. That'll be the velocity vector. Notice how I did it right here. If you play around with this on your own, after I put it on Moodle, common mistakes are people delete commas or delete curly braces or square brackets or things like that. You want it exactly as I have it. So now we're going to have not only the position vector in the picture, but a velocity vector too. You can see the initial velocity vector is pointing straight this way. It's always tangent to the curve, and it gets shorter, then it gets longer again. It's long when the object is going fast. It's short when the object is going slow. It's always tangent to the curve. Has a length equal to the speed at any moment in time. I can do more to this to pretty it up, but for sake of time, we only have 5 minutes. Let's consider a three-dimensional example. So what I'm going to do is I'm just going to copy and paste all this stuff down here and change, whoops. Okay, that worked. Change the number 2 to 3. This is going to be a 3D example. And it'll be bit more interesting if we maybe just use cosines and sines or something. Maybe cosine 2t for f sine 3t for g, and maybe h of t, a third component would be, I don't know, cosine 5t. My r of t now is going to have three components, f, g, and h. Still the same kind of code, though, except I added a third component. The velocity vector now has three components as well. It can be, these things can be evaluated at various moments in time, like maybe you want to choose, I don't know, pi over 6 or something. What's the position at time pi over 6? It's that. What's the velocity at time pi over 6? It's that. We can confirm that this way as well. You can compute limits. By the way, if you didn't, I made a pi by doing escape, p escape. It's also in the palette, the pi symbol. You can also make a capital PI for pi. All this stuff can be done in an analogous way, component by component. But now if you're going to plot it, you got to use parametric plot 3D instead of a plain old parametric plot because it's a three-dimensional thing. Let's go from 0 to 2 pi. There is the 3D parametric curve. That's the curve itself. But we can also try to do the motion. What can I change here? Just change the parametric plot to parametric plot 3D. I think I want to start at 0 instead of -2, so I'll make that a 0. Start B just barely bigger than 0, like 0.0001. Make this a 2 pi here. I need graphics 3D instead of a graphics. I need a third coordinate for the origin, 0, 0, 0. But I think everything else should be okay. Well, no, the plot range will be a problem. Maybe I can just do 1.2 here. That'll go from -1.2 to +1.2 in all directions. I don't think this axis true will do anything, really. So now we see the initial location of the object at time 0 in this case. That's the position vector, and evidently the velocity vector is going out of the box. And we can see the motion at any moment in time. I think the velocity vector is too long. Let me just scale it down. If I scale down the velocity vector by like a factor of 5 or something, that's probably a good idea. It's 5 times shorter than it should be, but it's at least tangent to the curve now. At any moment in time, I see the position vector and the velocity vector. And you can click on this and move it around to try to get a better feel for the three-dimensional nature of it. And even in 3D, if it was the correct unscaled down version of the velocity vector, still tangent to the curve here, but it would have a length equal to the speed. And yeah, what we're most interested in here, initially, starting in class on Wednesday, is, so we talked about derivatives here, is integrating these functions to find, well, integrating velocities to find displacements in 3 dimensions even. And also, ultimately, probably after the exam in a week, most interested in understanding this curve. And the best way to understand the curve itself is to also understand the acceleration vector, second derivative of the position vector. Because if you can understand the acceleration vector, you can understand what's called the curvature of the curve. And you can also understand forces. If this is like you on a roller coaster, the acceleration vector is going to be in the same direction as the force at every moment in time. So understanding how your object on the roller coaster accelerates gives you information about the net force on the car as it's moving around the roller coaster, which would come from sources like gravity, but also the normal force of the roller coaster itself and things like that. Okay. That's what we're ultimately after, though we won't get there until after exam 1, which is in 1 week.